Now I will open a SAP 2000 model. So I can just open it, for example, start a new model. Let me start with a two-dimensional frame, just for the purpose of demonstration of plastic hinges for beams. So I will start with grid only, and let's use the Newton millimeter units and the default material designations from US. So I will just click on grid only, and let's assume that we have a 5-story frame which is only in the XZ plane. So I just need only one Y direction grid line, and four, let's say it has 4 spans in X direction, and it is a 5-story reinforced concrete frame. Let's assume that the X direction spacing between grid lines or span lengths are 6 meters. Y direction doesn't matter because we don't have Y direction in it. It's a two-dimensional frame. And let's say the story height is 3 meters and the origin is 0, 0, 0. Let me click just OK. So here you can see this is my 3D view of my two-dimensional grid which I just developed. Let me go to XZ elevation, which is this one, and I will simply create one two-dimensional reinforced concrete frame with default everything just for the purpose of demonstration. But you should know that in actual case you will be using real values of your project. So I will be simply starting with define materials, and I have one material, default material for concrete, one for steel. Let me just add a new material, and let's call it, let's have it of concrete type. Let me modify it now, call it, let's say, concrete. So I'll just assume that the viewers already have the idea about the use of SAP 2000, so I'll be really quick and give some default values and go with that. So it's 27.5 megapascal FC prime, and I will just use default values and just define it. Similarly, I add a new material, and this time it is of rebar type, and let me just modify it, call it, let's say, rebars. And let's assume for this case that the longitudinal and transverse rebars have the same properties for simplicity, and then I just call it rebars. I click OK. Similarly, I define quickly the two frame sections, one for columns and one for beams. I import a new property, and let's have a rectangular, sorry, I have to add a new property and a reinforced concrete rectangular section. Let's assume that this is my beams cross section. Let's make it like 450 depth, and width can be 250, and let's call it as RC beams. RC beams, its material is concrete and its reinforcement is of beam type only. We can give a cover of, let's say, 60 mm top and bottom, and if we want the program to automatically calculate the moment versus rotation behavior using ASC 41 table, we just see in the table that the amount of reinforcement is required. The row value at top and bottom reinforcement is required. So therefore we have to give the information about reinforcement here in the beam cross section if we plan to use ASC 41 table automatically. There are two basic options in while defining a particular plastic hinge input properties. One is that you directly use ASC 41 table and the program takes care of that everything, and it just gives you directly the moment rotation behavior. The second is that you plot it yourself, you assign it point by point yourself, and in that case you don't need to provide the reinforcement because you will be manually picking the values from ASC 41 table and defining the whole curve by yourself. So in that case the program doesn't need to have the reinforcement, top and bottom reinforcement. So at both ends, left and right end of the beam, because the hinges can be assigned at both ends of the beam. The program is asking the top and bottom reinforcement. So I can just give like 0.01, like 1% uh, reinforcement, and similarly uh, it should be the cross sectional area of reinforcement. So it can be a number which is corresponding to your units of reinforcement area. So let me see what units I am using. I am using millimeter Newton, which means the cross sectional area of rebar should be in millimeter square. So corresponding to what rebars I have in my beam, let's say that I have uh, two rebars at the top, corresponding to, let's say, 25 millimeter diameter. So I can quickly calculate their cross sectional area. So I give this number, let's say, for both left and right. Let's assume for this case that it has the same reinforcement at both ends and no curtailing and everything. So I give this number here, top and bottom reinforcement, and this is a step which you generally do not do while defining a linear model in your SAP 2000, because the purpose of that analysis, linear analysis, is the design itself. So therefore you don't need to provide the reinforcement at the start of analysis. But nonlinear modeling requires to define the reinforcement, because the capacities of each beam and column in the form of moment versus rotation behavior need to be defined in a nonlinear computer model. And those capacities are a function of reinforcement. They depend on reinforcement, and therefore the nonlinear modeling can only be performed when the initial design is finalized and you already have all the reinforcement detailing with you. And the purpose is to check the performance of that design. So let's assume that the longitudinal and confinement both bars have the same material for simplicity in this demonstration. So now it is a beam cross section and the program already have the reinforcement with it. So I click OK, and similarly quickly add a new property called reinforced concrete columns. So now these are my RC columns, and let's assume that all the columns have the same cross section, all the beams have the same cross section. So it is, columns are, let's assume, 450 by 450. They are square columns, let's assume, and then they are made of concrete. They should be provided with all the property modifiers. For beam also I just forget, but they should be provided with all the cracked stiffness modifiers based on what building code you are using. So if you are using, yes, for reinforced concrete beams, if you are using ACI 318, it will be 0.35, and for reinforced concrete columns they will be 0.7 for both M2 and M3 directions. But more importantly, again, if it is a column, although in this particular demonstration we are not using plastic hinge approach for columns, but if you want to use it and want to use the program automatic calculation of plastic hinge properties from ASC 41, you have to provide the actual amount of reinforcement, the actual design of your column in this particular form. So just like beams, you have to define the materials for your both type of rebars, and then type will be obviously columns, and then the shape of your transverse reinforcement, and then amount of the longitudinal reinforcement starting from clear cover, the number of bars along both faces of your cross section. You can see that this is the 3 axis, this is the 2 axis. So using this form you can tell the program how many number of bars should be along both of the axes, and what should be their diameter. The same is for confinement bars. You can provide that information, and this will be used to for the definition of plastic hinge properties from ASC 41. If you provide all this information, so this information program will use to pick your applicable row or properties in the ASC 41 table of RC columns. So again, the last option is about the design. Since the purpose of this nonlinear analysis is to check the performance of the structure and therefore it doesn't matter what option we select, we are not going to design uh, our structure based on this analysis. So with this I will just simply click OK, and my RC beams and columns are defined already. Uh, and then the next step should be to quickly create that geometry, and then I will go to the definition of plastic hinges, which will be a new step in this particular demonstration. So let me just quickly create all the beams. So I select a cross section of RC beams and quickly create them for all the beams, and similarly for all RC columns I just select them like this, and the program will be able to quickly draw it for me. And then at the end I again select all the bottom nodes, actually 4 nodes, and then assign the joint restraint. We will assume that it has all the fixed support at the base, which means all 6 degrees of freedom will be restrained at the bottom. So now the geometry is quickly complete. Now currently this is a linear model. We have no plastic hinge in it or no inelastic component in it. So this will behave linearly. For example, for any beam at both ends, the relationship between bending moment and the rotation theta is forever linear. So if I apply some force P, horizontal force, which is unrealistically high, this model will give me an unrealistically high theta value or deformation value or any other response. It won't be able to predict the failure. It won't be able to capture the inelastic action or inelastic behavior of my structure. So therefore it has many limitations. It is a linear model. Now we want to convert, let's assume, it into a nonlinear model. Now we want this program, this particular frame to be a damage aware frame, which means if I apply some force which is beyond the moment capacity of a particular beam, the model should be able to tell me that this beam will fail under this load. In order to do that, we will be using the plastic hinge modeling approach, and this essentially means that we have to define the moment versus rotation behavior for each of these beams. There are like 16 beams in this frame. For each of those beams we need to define the moment versus rotation behavior at two ends. So which means we have to define actually 32 plastic hinges, and then we assign those hinges at the ends of each beam, and this way we can make it nonlinear and then run the nonlinear analysis and predict the behavior or failure of my RC beams. So there are again, as I have said, there are two ways to do that. One is a direct automatic way in which the program just directly takes the values from ASC 41 and define the plastic hinge curves, moment rotation curves for you for each of the hinge. You just need to select that option and assign it to each of your beam. Second is a manual way where you can define each plastic hinge manually one by one and then assign it at the ends or corners of each of that beam. So I'll show you quickly both of these ways. The first step should be to go to define, section properties, and hinge properties here. Again I would repeat that if you want the automatic hinge option, you must provide the reinforcement of your beams and columns or any elements while defining the frame section, right? So when you define a frame section, you have to provide the reinforcement if you want to use the automatic option from ASC 41. In my case, the beams already have that reinforcement. We just entered that. So I add a new hinge property. I should select its default type. Values for default is concrete type, and I click OK. And here I have to give the name of that hinge. Let me call it as moment rotation beams, right? So this will be easy to remember. Moment rotation beams is the name of that hinge which I am going to define. First step you have to select is whether that hinge is force controlled or deformation controlled. In order to explain that difference, let me just quickly show it here. The type of plastic hinge which I explained at the start of this session was by default deformation controlled, where you have actually defined the post yield behavior. So this is the yield, and after that you define these points. Post yield behavior, this is all, this behavior is post yield. After yielding behavior you define it, you give the deformation values for different points on x-axis. For example, you know that this distance is small a, and then up till the last point, let's say it ends here, the last point, this is small b, and this height is small c. And similarly you know that there will be 3 IOLS and CP values, and they also will be in form of deformation. So all the inputs are in the form of deformation, and you are relying on the ductility of your beam in order to get a good performance, right? So it is called, this kind of beam, this kind of plastic hinge is called ductile type, or deformation control type, deformation controlled. And the reason is obvious that actually this particular beam, we are assuming that it can have some level of deformation before complete failure. So that deformation capacities are defined by these small a and small b, and therefore it is having a ductile behavior. It is not that after yield point it suddenly goes down and fails. It is having a ductile behavior, and it is deformation controlled. But one thing I should explain here, that see, these are all modeling assumptions. They should be in complete conjunction or agreement with the actual situation of your beam also. For example, if you assume that these two ends of this particular beam have a ductile plastic hinge, it by default means that your actual beam also will be having a ductile detailing at these two ends also. So if you have a real beam and you are giving this behavior, which is a ductile behavior, to your plastic hinge at both ends, it means that in real beam also you will be ensuring that it will have enough detailing, ductile detailing at both ends, so that it can develop that behavior. So actually it's not just one modeling assumption, it actually comes from your actual design also, right? Or in other words, if you have a modeling assumption, you should ensure that in your design also, right? So therefore in real design of special moment resisting frames, for example, where you have um, ductile detailing at certain points, those areas are called like plastic hinge lengths, or designing a plastic hinge. By designing a plastic hinge means that you actually ensure that ductile behavior which you assumed in your modeling, right? So designing plastic hinge, you should keep that in mind, that this is the actual design and this is the modeling assumption, right? They should always be in agreement, otherwise your analysis will be completely wrong, it will be deceiving. So therefore please keep that thing in mind while having all that discussion, and keeping that in mind. So I come back again to the plastic hinge types. So this is by default one, the one which I explained was deformation controlled or ductile type. On the other hand, you have another type of plastic hinge, or you can say a hinge which I think it shouldn't be called plastic, it can be just called hinge, um, and that is brittle type. Brittle type means, or it is also sometimes called as the force controlled. Force control means that you can, for example, take the same example of moment versus rotation. So here also we will be providing a moment versus rotation behavior, but not the complete behavior. We will be simply telling the program that okay, this is my moment corresponding to my, and since it is a brittle type or force control type beam, it is by default, the program will by default assume that the beam will simply fail after that moment, right? It won't have any A or B, or it won't have any deformation capacity after yield point, right? So in this particular case, all you need to define is just your my or your yield capacity, right? And then you define this hinge and define it at both ends. But if you define this particular plastic hinge, brittle hinge at both ends, after the analysis you won't be able to see what level of nonlinearity your this beam have experienced. All you can do is to detect whether the beam has yielded or not. Since it is assumed brittle failure, so you can simply detect whether the beam failed or not, whether the moment in the beam exceeded from my or not, right? So I repeat again that this brittle hinge will have just one input, and that input in this particular example will be simply my moment capacity of my beam. If this is shear type brittle hinge, it will be shear capacity of your beam. If it is like torsional or axial type, then it will be their corresponding force capacities. So I can write in general that it has just one input, and that is force capacity, moment or shear or axial load or torsion, etc. But a ductile hinge will have many inputs. It will have the complete post yield behavior in the form of ultimate moment, yield moment, the deformation capacities up till the failure point, right? So if you want to just detect the flexural failure or detect the shear failure, you can use brittle hinges. Or your actual behavior is not having the ductile failure at the ends, it is having non-seismic detailing, it is having, let's say, brittle detailing, or expected to be failed in a brittle manner, then you can use the brittle type plastic hinge in the modeling. So now I go back again and select, for example, let me just start with force control type and then look at the list of all the hinge types which are available. You can see here that there is an axial hinge, V2 V3 hinge, torsion, M2 M3 hinge. So all these 6 hinges are actually corresponding to the 6 actions which my frame sections can have. And then after that are the interacting hinges. Interacting means that they are the combination of any of these two actions or three actions. So for beams, we can use any of these first uncoupled hinges or individual hinges for each action separately. But for columns, for example, we may use either if it is a two-dimensional column, we may use either of these three hinges, or if it is a three-dimensional column, it will have a complete interaction of all the two moments and axial load. Then I will be using this interacting PM2 M3 hinge. If I am using fiber modeling approach for columns or shear walls, I will be using this fiber PM2 M3 hinge. And then finally there are two kind of parametric hinges, a kind of shortcut ways to define the concrete and steel hinges for beams and columns. So actually they are for columns because they are interacting PM2 M3 type. So if I just talk about beams, and I only talk about the flexural nonlinearity, I will be actually using this moment M3 hinge type. And since it is a force control hinge, the inputs required by the program will be simply force controlled inputs, which is actually just one main input, and that is the maximum allowed moment. That is the moment capacity of your beam, as I have mentioned. And another input is actually the three acceptance criteria. So you give a ratio of moment caused by the applied loading to the moment which is allowed, which is given this number on top. And then you can detect after the analysis, uh, if you give one here, which means that the ratio of moment versus uh, maximum allowed moment have exceeded 1 for all the elements which are shown here with the red color, which means the applied moment have exceeded the capacity which you have provided. So just to have a quick overview again here, so I repeat that in the brittle hinge type, you are just giving like this point only, and after that is the program assume that it is failed. So M3 versus theta 3, obviously if you have 3 axes like this is your 3 axis cross sectional axis, this is your 2 axis. So the primary bending moment for this beam will be M3, moment about 3, because the beam will bend like this. So you can see from the right hand rule that the primary bending of this beam will be M3 in the M3 direction and theta 3 direction. So if you want to define a flexural plastic hinge for beam, it should be M3 type, and the input required is a relationship between M3 and theta 3. But again, I will repeat that this initial elastic part you don't need to give. So I should actually write it like this: M3 versus theta 3, the rigid plastic hinge I have to define. So it is asking me just this number, My. And again, it has two options. One is automatically program calculated, I will show you in that same form, or user defined. So user can give this number, and it is asking you this number and the three numbers on this particular you know linear part. You can say this is actually these three numbers. So the actually they will correspond to IOLS and CP values. So if I go back and show you the same form, which is let me just show you that form. So you can see here that first option is for moment capacity or maximum allowed moment. The first option is that I just specified proportion of yield moment, right? So the program will I just have to give that the ratio between moment and yield moment, or proportion of the yield moment. So one means that you just use the yield moment equal to yield moment. uh, the second is that I provide user specified moment, so I manually provide the capacity, right? First option, the program automatically will calculate because it already have the cross section size, already have the material properties, and already have the amount of reinforcement. So therefore it can calculate the moment capacity for me, and one uh, as a proportion means that just use that yield moment as the maximum allowed moment. Otherwise I can give my own number here. If I go for the first option, then I have to give three acceptance criteria as a ratio of moment divided by the maximum allowed moment. So m over my is the value which I have to give here. So one means that m is equal to my. So when your applied bending moment will be equal to the number equal to the my, the program will consider it as collapse prevention. I can change these numbers also, but they simply means that green color elements will simply mean that 50% of their capacity was used. It For blue it will be meaning that 80% of the capacity is used, and red will mean that their capacity is fully utilized and now they will be failing in a brittle manner. So you can change these ranges also, but generally this is the thing which you use. If the beam is not symmetric in both positive and negative directions, then you can uncheck it and give the negative yield moment. Sometimes the reinforcement at top and bottom is not same, and therefore you have a different positive moment capacity and a negative moment capacity, and corresponding ratios in order to check the performance after the analysis. You can also change them if you want. So this is how you will be defining a brittle moment rotation hinge for your beams. But again, this beam will simply able to detect in terms of forces whether the value exceeded the moment capacity or not. It doesn't capture any you can say deformations or any deformation related performances. But if I select deformation type for the same moment M3, now the form will be different. Now the form will ask from me three or four basic things. Actually, you can say 1, 2, 3, 4, 5 and 6. 6 basic things it will ask as an input to completely define the nonlinear moment versus rotation behavior for my beams. Uh, the first is the type of hinge. It can be a moment versus rotation or moment versus curvature also. Curvature is a deformation property for cross section, right? So moment, if I see this moment as an action applied to a cross section, the corresponding deformation will be uh, curvature. But if I see it as a deformation applied to the full member, it will be the rotation. So let's assume that I am looking at a beam from side or elevation view. You can see this is a side view before deformation or before application of bending moment. But let's say that it deforms like this after the application of bending moment. Let's assume that it deforms like this. So then uh, the points A and B, the line joining A and B was completely vertical, let's assume in an undeformed shape, but it won't remain vertical. It will become like this: A dash and B dash, A prime or B prime for example, in a deformed shape. The angle between AB and A dash B dash, that particular angle here, is the curvature or deformation of your cross section, right? So you can define this at you can say the nonlinear behavior between moment and the deformation at cross section level. You can define in the form of moment curvature behavior also. But when you talk about the full member level, you need to define the end rotation as the deformation. So that will be m versus theta. So the again the flexural hinge M3 hinge can be of two types, whether you define the relationship between moment and curvature or moment and rotation. So ASC 41 actually by default use moment versus rotation behavior for nonlinear modeling. So this is what we are following in this demonstration, but it can be of curvature type also. But curvature, the program use it to convert into the rotation, and in order to convert from curvature to deformation, the program requires what we call as the plastic hinge length. Plastic hinge length. So therefore, if you go for this curvature option, you should also give a plastic hinge length to the program to convert it into the rotation. But if you are directly using this rotation option, then you don't need to provide the plastic hinge length. So let me just quickly go back to SAP 2000 and show you that if I select moment rotation, then I don't need to define this hinge length. But if I select this moment curvature, then I have to define a hinge length as a proportion of the total length of the beam, or I can give an absolute value by unchecking this relative length option. So but we will be going with the type of hinge as the moment rotation. So our relationship between moment and rotation. If I go to curvature, you can see that it changed to curvature now. So how we will be defining the basic backbone or basic moment versus rotation curve, this solid black line, we will be defining it as moment divided by a scale factor on y-axis and rotation by a scale factor on x-axis. And that scale factor we will be providing here, that can be those scale factors can be the yield moment and yield rotation. So again I can show you here that actually on y-axis it will be m over my. So if I just redraw the same figure it is moment divided by scale factor, and theta divided by scale factor. Now scale factor we can just give in the program as my, yield moment, right? So the program will simply use m over my on y-axis. So my curve can start from 1 and then it goes to some number higher than 1 depending upon what is the difference between yield point and ultimate point. Maybe like 1.2. If I just put 1.2 here for this point, it means that I have a 20% over strength in my beam up till ultimate point. Then it go down and then it becomes flat and then it becomes exactly 0, join the x-axis. The scale factor for the x-axis can be 1 because I directly want to start my curve from the yield point. So this point is already my theta y, right? My origin is already theta y. So which means that scale factor I can just use as 1, and then in that case I will be simply using this number as small a and this number as small b directly coming from ASC 41, and this height I can simply have small c because I already have m over my at my y-axis, which means that this small c is already the ratio between the moment, the residual moment capacity by the actual moment capacity. So therefore uh, this height can be simply equal to small c from ASC 41. So this a b c can come from ASC 41, and we define the curve in such a manner that we use my as a scale factor on y-axis and we use 1 as a scale factor on x-axis. By using this form of the curve, we can simply give the coordinates of this point as x coordinate will be small a, y coordinate will be let's say a number higher than the yield point, maybe like 1.2, 1.1 or something like that, depending upon what is my mu, right? And the coordinates of this last point will be uh, x will be small b, y will be small c, right? And we can have a strength loss here and we can decide about how much stiffness we should give while having a strength loss, and other inputs we can just uh, define it while defining the shape of the curve. So I go back now and let's see that what are the default values which are here. Since I have selected symmetric option, which means I will just be allowed to define the curve on positive side and the negative side will remain same. Positive moment versus theta and negative moment versus theta. If I uncheck it, then the program will allow me to define the negative side also. Point A is the origin. So this is the A point on the origin where my cursor is now is 0 0. I cannot change it. This point on top is by default it has a coordinates of rotation is positive, the y-axis is positive 1, rotation is 0. Negative point side, if you see, this is -1 and rotation is 0. I cannot change this 0 because it is by default a rigid plastic hinge, so it will start from y-axis directly. No need to provide the theta y for positive and negative sides because the program can automatically calculate it. It has all the inputs required to do that. So the hinges will only be activated once the moment in that beam will exceed the my value, which is m over my will exceed the value of 1, right? So therefore we give -1 and +1 here. So the point A and point B and point positive B and minus B, these 3 points which I just selected, they are almost fixed for all the hinges. You most of the times do not change. M over my will remain your yield point on positive and negative side. Point C and D will obviously will change. C is the ultimate point uh, and D is just below that where there is a strength loss, and D is the last point, the pink point, right? So the curve which this program is using, it is not reducing the strength gently which I was showing you. So it is not m3 theta 3 like this. It is not like starting like this and gently going down. It suddenly goes down and then goes to the residual and then go back to origin, or the x-axis, right? So but you still have some control on its shape. If you want, you can uh, change it, but in this particular case, if you are using this shape, like starting from here then suddenly down and then this and this, in that case you need to define just this point, this point and this point. This point is already your uh, this is m over my, and then this point will be your x will be your 0 and y will be your 1. For this particular point, your x will be small a, y will be your value slightly higher than 1, which is corresponding to your ultimate point. So if let's say your ultimate mu is 10% higher than your my, obviously you have to calculate it yourself based on the expected material strength. If you use the nominal material strength, maybe you can use it as my, and expected you can use it as mu, which will be 10, 20, 30% higher than your my. So it will be, for example, 1.2 or 1.1 my. This the coordinates of this will be small a and small c, because the height is c. The coordinates of this last point will be small b and small c, right? So if you look at this shape, only you need to require my, mu, small a, small b and small c to completely define this backbone curve, right? So these are, you can say, the 5 inputs which you would want to define this particular hinge. So let me go back now to SAP, and so similarly, so this will be uh, y-axis of point C is your ultimate moment in positive 1.1 minus 1.1. So you are telling the program that my overstrength in moment is around 10%, and then this is your small c, which is the height or y-axis corresponding to the D point, which is this pink point, and positive and negative same number, and this is your 0 point minus 0.015 is actually your small b value, right? uh, Actually this should be small a and this should be small b. C value should correspond to small a, and then the e value should actually be corresponding to small b. So 0.015 for both of these points are actually your small a, and for e value, which is e point, which is the last point, the red point, you will have a coordinate as small c as your y-axis and small b as your x-axis. So let me just quickly, okay, it is erased already, but you can see that this last point is simply cb. This is your mu over my, actually the overstrength, sorry, this is c and a. This is your mu, how much your mu is more than my, and this is small a again, and this is the yield point. So now this displacement, force versus deformation behavior, or moment versus rotation behavior is clear, and obviously in conjunction with that you also have to provide the my. Obviously without my this curve won't make any sense, so here you will be providing my. For y-axis, you can either use the yield moment automatically calculated by the program, or you can uncheck it and provide your own scale factor, your own values of my in positive and negative directions. So again, two options: automatically calculated, or you can uncheck it and give your own numbers. You manually calculate your moment capacity in positive and negative sides and give the number here. Uh, for the rotation, the default rotation scale factor is 1. If you want to use a convenient way to use the ASE 41 values of small a, small b and small c. Otherwise you can give your own scale factor also, but I won't be going for that option. This option is asking whether the load carrying capacity after point E, which is the last point, red point, it should continue to remain that same strength for indefinite amount of deformations, or it should just drop to zero. So I think this extrapolated option is better, because if for example you drop it to zero, it can cause some numerical error sometimes. Anyways, once your beam cross the point E in positive and negative direction, any of the direction, you can imagine that it is completely gone. It is completely failed, right? But sometimes dropping it to exactly zero can cause some numerical error. So maybe you can just go for the second option. But it's just a matter of how the program should treat your beam once it goes beyond point E. This is the acceptance criteria in positive and negative directions. The theta IO, theta LS and theta CP values for positive and negative sides of the moment. Uh, you can check this symmetry, and in that case maybe no need to give the negative my or negative the acceptance criteria. In that case negative will be same as the positive values. So this is theta IO, whatever you get from ASC 41, theta IO in the negative side, theta LS, and then theta CP and theta CP. Obviously your the ASC 41 uh, doesn't provide the negative and positive values separately, it just use the same table. So obviously you have to see whether you are using top reinforcement or bottom reinforcement to actually go into that table and pick the number. If you are going for negative reinforcement, actually you are using the same table for negative IU, LS and CP. So these things are covered already. Now the last thing left in this form is the hysteretic type and parameters. Here you are telling the program that if my beam is subjected to reversal of forces, if it have to unload from a particular moment or and then reload from a particular moment, how it should behave, what cyclic behavior should be given to my uh, particular plastic hinge or my particular beam. So for example, if you are giving M3 theta 3 behavior, and this is your starting point, this is your ultimate point, then you are dropping it, and then this is your last point, E point. So you will be telling the program that if for example the moment in my beam is this number, and suddenly the load changes its direction from this A, the suddenly the force changes its direction and the bending moment changes from MA to some minus MB, some new number in minus. So obviously uh, the behavior is simply in one direction or in the other direction, like this. If you just give for example, okay, sorry, like this. So if you are if your applied force change from this number MA to some number in minus, let's say MB, on this negative axis, minus M3, how the program should change the behavior from positive moment to negative behavior. So should it follow this line to go to your new MB, this let's say is minus MB, or it should follow something like this to go to your MB, or it should follow like this. So we have to tell the program about the cyclic behavior. Cyclic behavior, also sometimes called as the hysteretic behavior, right? So we have to tell this program to the program along with the backbone. So the behavior, the force deformation behavior which we have defined is backbone. Now this backbone should always be associated with a cyclic behavior also in order to completely define it. Otherwise program will not be able to handle the reversal of forces and how the force change in case of the changing of direction of applied forces or applied bending moments. So there are different shapes available. For example, one is the elastic perfectly plastic. So it follows the same initial stiffness as while unloading, and then it yield in the other direction, and then it follows the same initial stiffness while reloading. So this behavior is called EPP. There can be a behavior like flag shape behavior, which yield, and then when it unloads it doesn't go back to origin, it follows this line. So this is called a flag shape hysteretic behavior. There can be some other types also, like pinching behavior, like which goes close to the origin and then again follows like this and then again come back to the origin or pass close to the origin. This phenomena is called pinching. So this is also one hysteretic behavior. So there are different behaviors which are available in different software, which you can assign to your backbone curve. But SAP 2000 also have some 6 or 7 behavior, and we have to understand their shapes in order to use them. Some of them are suitable for metals, some of them are suitable for concrete. For example, this EPP can be suitable for steel material or a beam made of steel, but it is not suitable for a beam made of reinforced concrete. So for reinforced concrete, different researchers have developed experimentally testing the beams and then develop those hysteretic behaviors. So one of them, for example, is called Takeda uh, model, and there are different others also, but this Takeda one is available in SAP 2000, and you can associate that with the plastic hinge of a reinforced concrete beam. It looks like the typical behavior of reinforced concrete beams, something like this, which the reinforced concrete beams generally follow. It has some parameters which you can control, and there are some other hysteretic behavior which are mostly suitable for metals. Some are suitable for other kinds of elements. So let me show you that list of cyclic behaviors which are available in SAP, and you can associate them with the plastic hinge of your particular uh, element. So these are the hysteresis type: isotropic, kinematic, Takeda, pivot, concrete, BRB, hardening, and degrading. So I would suggest you to go to the analysis reference manual of SAP 2000. So let me just quickly cancel it and go to the analysis reference manual of SAP 2000, and there you can see the shapes of each of these behavior and the controlling parameters of each of these behavior. So that is important to understand. So I'll go in the help and in the documentation, and in the manuals I will be selecting analysis reference manual, this one. So I double click it and it will directly open. It is also saved as a PDF in the same directory in which the SAP 2000 is installed, and in that I can go to, for example, which chapter, let me see, um, material properties chapter 6, and in that chapter 6, and in that you can see here these are the hysteretic models, uh, this particular section, and all of the hysteretic models are explained here, and you can click on this and go to hysteretic models. It will first show you how you can define the basic backbone curve, the action versus deformation, which is the M3 theta 3 curve for our case. Then in the cyclic behavior, it explains all the hysteresis type. For example, how the elastic hysteresis type would look like. This is kinematic. Then degrading hysteresis model, this is how it looks like, and then this document also explains all the parameters which are required to completely define that behavior. Similarly, I can see this one is which one, this is degrading type with some different parameters, and then this is Takeda model. This one is mostly suitable for reinforced concrete elements. Then this is pivot model. You have more control on this model because you can so-called pivot your model to certain points which you can provide as an input. This is how the concrete hysteresis model look like. You can see the compression side and negative side suitable for modeling concrete material, but you have to provide an energy factor for that also. Tell the program how the stiffness degrades with different cycles. This is the BRB hardening, obviously not suitable for concrete, but as the name suggests, you can use it for buckling restraint braces. This is isotropic, and then you can see their details and everything. So I will simply come and select the Takeda model for my reinforced concrete beams. So I again go to define, I was here, hinge properties, and in that I have to add a new hinge, select, and let me just call it moment hinge for my beams, right? Moment hinge beams, and let's select M3, and here I was selecting a hysteretic type, so let me just select Takeda model, and for this model you don't require any additional input, but if you select for example concrete type, you have to provide an energy degradation factor. You can see its details in the analysis reference manual. Similarly, for pivot model there are several inputs required. For degrading model there are a lot of inputs required for that. So here I am just selecting, let's say, Takeda model, and let's assume for this demonstration that all these numbers are correct for my particular reinforced concrete beams. I have selected them from ASC 41. Let's assume that the acceptance criteria for both positive and negative sides, if I uncheck unsymmetric, let's assume that it is same from ASC 41. So I'll just click OK and use the automatic option to calculate yield moment. So program will take care of that automatically, and let's say this option, and let me click OK and then click OK again. So now I have defined a plastic hinge for my beam, and let's assume for this demonstration that all of the beams will have the same reinforcement, the same everything, and therefore the same hinge is applicable to all of them. If I can click on show hinge details, the form will be expanded and you will see its detail also, like its type, its behavior, and whether it is generated by the program automatically for a particular beam or user have defined it. So when it says no to generated, it means user have defined it, and it is not generated from any other master hinge, so therefore this is blank. If I click on show generated properties, so currently there are no automatically generated hinges by the program. So I can click OK, and if for example I want to assign this hinge to a particular beam, I can select that hinge and go to assign, and then go to frame, and then in the hinges option I can go there, and then here I have to select the hinge property from the list of available hinges. I can select the one which I have just defined, and I have to select the location of that hinge. It can be relative to clear length. So when I say 0, it means on one particular end, and then if I just use a particular distance, in that case I can give a distance also from that end, but when I say relative to clear length equal to 0, which means exactly at the left end. If I want to assign this beam, this hinge in the middle of my beam, obviously I can either use 0.5 here, or I can actually give that distance by using a different option. From one end I can give a distance that okay, this much millimeter it should be assigned, but currently I want it to be just at both ends of the beam, so I will just use relative option and 0 relative distance, add that hinge, and on the right hand side I can select the same hinge again. Let's assume that it is applicable, and I will select 1 and then add it again. So 0 and 1 means at one end and on the other end, right? So two hinges will be automatically created by the program from this master hinge which I just defined by this name, and it will be assigned at the both ends of my this selected beam, right? So when I click apply, you can see here that uh, two green color additional elements are introduced in my beam. Obviously, although they are not exactly at the corner, but this is just a matter of representation. They are actually in the zero length elements and associated at the extreme ends of that beam. It's just a matter of visualization. So one hinge is called 1H1 and other is called 1H2, right? So it automatically named, the program named those two hinges, and in the brackets it is showing which hinge was used to create those additional auto generated hinges. So if I now again go to define section properties and go to my frame sections, go to my hinges, define section properties and hinge properties, and if I check this show generated properties option, you can see that these two additional hinges are uh, automatically created by the program, and now their generated option is yes because they were generated from my input, the one which I defined, and they are generated from the name is exactly the same as the one which I give here. So this, the first one which I defined, was used as a master hinge, a kind of a template for all the auto generated hinges, right? If I want to see a particular automatically generate hinge, I can select it and go to modify show property, and then again modify show hinge property. Here I can see that the behavior is same as what I have given. Model is same, Takeda. All the acceptance criteria is same, but the only difference is that now I, in that master hinge or template hinge, I use the yield moment option as checked, but now the program is have actually calculated the yield moment capacity in my units Newton millimeter, and and put the number here. I cannot change it, but you can see here that program is have automatically calculated the yield moment based on the material properties I assign, based on the cross sectional properties, and based on the amount of reinforcement. These positive and negative moment capacities are calculated automatically. Similarly, on the other end also, since the reinforcement was provided for both ends, program was able to calculate the moment capacity for positive and negative sides, because the reinforcement was also assigned for positive and negative sides. So you can see that you can confirm the properties of hinges by going again to define frame sections and then define properties, define hinges. So I can just cancel this form, and that's how you can manually one by one define a particular plastic hinge and then assign it to your beams. I can do it for all the beams in this model. So that was one way to define the hinge properties, and that was kind of a manual way also, because you are supposed to pick the IOLS and CP acceptance criteria and the small a, small b, small c, the modeling parameters from the ASC 41 by yourself, and then assign it in your program. But there is a more direct way to do that also. In that case, the program can directly pick these values from the table of ASC 41, but obviously then you will have a limited control on the properties of those hinges.